following Friday is the celebration of research. We will not be having eigen here at 12:30. We have the plenary presentations in Yuval Auditorium. You'll receive eigen credit. If we convince the chair of the math department to allow you to have eigen credit, I don't have anything to do with the fact that for husband, you can do off speaker. For the celebration of research. So we have 4 plenary speakers starting at 12:30. These are the 4 award winners of the Siegfried Horn Excellence in Research and Creative Scholarship.
Welcome to Eigen Talk. It's my pleasure today to introduce to you my younger brother, Joshua Barrow. He also happens to be the younger brother of Dr. Burdick. I guess the transitive property would say that makes, what, Dr. Burdick and me brothers and sisters? Well, we are, because all 3 of us did research with Professor Ray Hefferlin at Southern. He was our first research mentor, and sadly he passed away last March 7th. We have here his last research student. Josh was doing research with Doc in the periodicities of triatomic molecules, and he's finishing their last paper together without Doc. And he graduated from Southern in May and won fellowships to several universities to do a PhD in physics. He picked the University of Tennessee at Knoxville. He has a named fellowship there, the Berthoff Fellowship. He's interested in studying theoretical particle and nuclear physics. Although in math and physics we always have the option of changing our mind in the first couple of years, unlike some other science fields. So he's got a great career ahead of him, great start to his career, and I'm really pleased that he can be here to talk to you because it's always inspiring for those of us who've done this. It's inspiring and fun to look back, and for those of you who are looking ahead to all this, soon to be Professor Barrow is a great model for all of us. So please give him a warm welcome.
And thank you to Chandel and Margarita and obviously Dr. Burdick for having me, along with the departments here. It's a treat to finally come north. I've been at Southern all my life, pretty much, so it's a very different atmosphere here. You guys have changing colors. We don't have that yet. So anyway, I am at the University of Tennessee. I'm a first-year graduate student. I'm not currently doing this research any longer. I finished this back in, actually right before graduate school started. We just have a few last things to do before we present this paper, and then it'll be submitted to the International Journal of Quantum Chemistry, where Dr. Hefferlin was previously published and actually got the front cover. So we'll actually show that, and we'll talk about it a little bit. So I am going to be talking about periodic trends in triatomic molecules today. Don't worry, that'll be explained. But just to go over a little bit of background so that everybody's on the same page, I know that a lot of you don't necessarily have backgrounds in chemistry. I had a chemistry minor, so I'm one of those people. But this is just a little bit on that. So when I say triatomic molecule, or if I say diatomic molecule, what do we mean? Basically, di, 2, tri, 3. Okay, I have a few examples. We have, of course, oxygen, thank God for it. And then we have water, thank God for it. But the purpose of this is that we want to understand not these very basic molecules, but much more complex ones, possibly ones that don't even actually exist in the laboratory. And that's what we're going to be talking about today. So these constituencies of 1, 2, and 3 need not be the same. That's the point here. Also, I just want to talk a little bit about spectroscopy and identification of elements. So if you guys have had, hopefully, your first course in physics and in chemistry and biology and everything, you've probably learned a lot about transitions between lower and higher energy states of elements, if not molecules. if you've taken a biology class, you've learned that it's this exact kind of stuff that allows photosynthesis to occur at a very fundamental level. The point here is that you can have absorption or emission of photons, and that corresponds to absorption and emission lines in spectra. And that allows you to do different identifications. The identifications can take place due to these discrete energy jumps and can be associated in this particular case with visible spectra. So if I'm looking at the hydrogen spectra, I have nice Balmer series lines here that can all be translated into beautiful colors. But if I look at more complex objects, for instance, like the sun, I have a lot of spectra. Now the sun is mainly hydrogen. We know that because of the intensity of the lines. But we also can look at all the other smaller constituents of the star based upon the black lines, the absorption lines, and all the other colors that we see there. And we can see basically abundances of elements in the sun due to fusion reactions. So the point is that we can use this spectra to identify elements. But we can also go further, and we can talk about molecules. We can talk about especially diatomic molecules because they're relatively simple systems. Hopefully, some of you will get a chance to take an advanced lab course. One of the things that I did in my advanced lab course at Southern was actually something that dealt exactly with the transitions of the nitrogen molecule and the nitrogen spectra. And the way that you can do it is you can create a model based upon something called a Morse potential. And you can basically say that the transitions of this molecule are analogous to transitions of an atom. So I have higher energy states here and lower energy states here. I have, if you will, in the Bohr model, higher, larger end states going to smaller and smaller. So what matters in transitions with molecules is that the wave functions of those molecules, of the entire system, and it's a many-body problem, so we can't really talk about the wave function, but the point is that the state makes a transition. And the state really matters at the beginning and at the end whether or not they overlap, okay? It's called a projection in higher level physics. But basically, you would say that the probability associated with one transition or the other is based upon the Fourier coefficients, but also that also corresponds to basically whether or not this amplitude here is overlapped with this amplitude here. So I can make this transition quite easily, but it wouldn't be very probable to transfer from the ground state here to, say, to the fifth state here because it's not overlapping. Okay, it doesn't mean it's impossible, it just means that the probability goes down as the square, actually. From here, we can go into something called Frank-Condon factors, which are important for understanding, especially diatomic molecules, and was the subject of a lot of Dr. Hefferlin's research recently. And Frank-Condon factors are basically the evaluation of the probabilities of these transitions occurring. So I would say maybe it's 50%, 0.50, that this guy here, going from the zero ground state of this higher energy Morse potential to this lower energy to 2, I give that 0.5. And that's based upon the intensity of that transition known experimentally, actually. We can do this for diatomics. Technically speaking, we can do it for triatomics, but the problem is that no one collates that data. No one has it all anywhere. It's not, we can't find it. So we'd either have to make it all ourselves, which would be incredibly expensive, or we had to turn to something else. So this works for diatomics, but when we want to talk about triatomics, it gets much harder because you have an entire new degree of freedom in your system. So instead of talking about Frank-Condon factors, we instead talk about a related quantity called vibration frequencies. You can think of these wave functions as having a certain kind of vibration frequency, except with a diatomic molecule, there's only one. Because if I have two atoms, they can just bounce back and forth together. But if I give another degree of freedom to the system, rather than make it go along a line, I make it go along a plane, and I have my head as the central atom, I can have a longitudinal symmetric state, which is where I have two outer atoms and they're both bouncing back and forth in a line. Or I could use that second degree of freedom and go transversely upward and downward. Or I could do asymmetric longitudinal, which would be back and forth. okay? And technically speaking, that's if you assume there's planar symmetry. You could technically have three-dimensional symmetry, but we say that you can ignore those just based on energy, that there isn't that much energy in those extra vibrations in the 6 degrees of freedom, 6-dimensional phase space. Anyway, the point is that the 3 modes are the main constituents of all the possible ones. And we can study these rather than the Frank-Condon factors, and then we can also talk about, for instance, the bond lengths of the molecule. We can talk about the bond angle of the molecule, every kind of characteristic of the system, basically, other than some of the more chemically interesting aspects like heat of formation, et cetera, which have already been done, actually. So that's why we aren't focusing on it. But anyway, the point here that I want you to understand is that it's inherently quantum mechanical, though. And what we're going to be looking at is an application and really a synthesis of all that quantum mechanical knowledge into a huge subset, or sorry, a huge, not subset, but a huge set of different values from our experiments and computations. So here are those visualized, and I just want to share that there's my less interesting head there. And anyway, the point is that the longitudinal frequency here goes back and forth symmetrically. And these were originally investigated in the diatomics with Dr. Hefferlin's work, but we don't really care about them as much as the actual transition states. So we have to make an approximation from the triatomic point of view to extend his work. His work in diatomics was interesting, and why it matters is because it allows us to talk about very interesting objects in the universe. So he, in his previous work, and I'll show a slide here in a second, looked at diatomics and basically was able to evaluate almost every single diatomic in existence, at least from the main group elements. And the reason why we care is because they act as chemical markers. The more that we understand the fundamentals of diatomics, triatomics, pentatonics, et cetera, small molecules, the better we can understand all of the objects in the universe. Because this, the Crab Nebula, a remnant of a supernovae, is basically a molecular factory. So if I know anything about what exists in the state that I can see now, and I can do dynamics, and I can play back the stuff, I could, technically speaking, I could figure out maybe what kind of star was there before if I didn't see it blow up previously. And then you can start talking about, okay, not just dynamics of one star, but systems of stars and galaxies, and you can talk about the entire evolution of this. So, evolution, a good one. So the point is that we can talk about supernovae, and they can be used, these different molecules, as optical precursors. And we can figure out where all this stuff came from. And we can better understand the universe that way. So it's relatively fundamental work, but it has a lot of applications. So the problem is that in these very dense, hot, high-pressure situations, our understanding of chemistry doesn't work. Because we can't, most of our chemistry is known experimentally. It's, Newton was the first alchemist, right? Or the last one, actually. And, gave birth to not only physics, but in many ways, chemistry. And you can't make these kind of conditions on Earth. So I can't produce all the spectra that I would need to actually understand all the different parts of my supernova here. And one group at UCL, at University College London, actually looked at the Crab Nebula and they found an argon molecule, okay? And if you guys, you don't have a periodic table here, but if you guys were to look at the periodic table, you would find that argon is in the noble gases. It's not supposed to react with anything. But somehow we've created conditions where it's stable, and there's a lot of it, enough that I can measure it tens of thousands of light years away, okay? These are not small things that are happening. So the point is that we have to go beyond what we can do experimentally and go into the realms of theory possibly to really understand this. And that's exactly what we're going to do. So we have stability under certain conditions that we have to take into account. So if we think about all that and we say, okay, let's just try to understand a system. One of the easiest systems that we can understand, and one of the reasons we teach it in mathematics, is sines, cosines, etc. Things with periodic nature, okay? Things that repeat themselves. So if I can understand a more complicated system in a way that makes me evaluate the system as a series of time-independent oscillations, or a tendency for some of those properties to simply repeat themselves in some period of time or in some kind of space, then I can better understand it. That's exactly what Mendeleev did with all of his periodic tables, okay? So if you think about what Mendeleev did, Mendeleev simply said, if I drop sodium in water, it looks a lot like potassium being dropped in water. I wonder if that's because of something. And then he arranged them just because in the particular arrangement that he did. Little did he know that when Schrodinger came around, suddenly Mendeleev made a lot of sense because both of them have the same kind of electronic structure, okay? But at the same time, he didn't need that. That's the real point. He was able to extrapolate that completely. So the trick is that if we choose to arrange the values in some particular way, that we see structure, maybe that structure is caused by something, okay? That's the point. So we're going to be using all of this in better understanding what all the big problems are going to be. So here's a periodic table in your room now. If you look at the periodic table, as we can see, it's arranged. There's your sodium, there's your potassium. They have similar reactivity. And if we look at the way it's arranged, it's not, at least to most laymen, it's not very periodic. If you actually look at the full periodic table, it's this weird, I have a tall block here, and then there's this long, thin block, and then it does this stuff, and then it does this stuff, and there's all these colors. Whoa, what's happening here, okay? The point is that when we talk about periodicity, what we really mean is the numbering scheme. The numbering scheme is what matters. And if you guys have taken introductory physics courses, you know that, for instance, the numbering scheme that we use is the number of protons. Of course, Mendeleev knew nothing about protons at his time, but he still was able to use a numbering scheme. So it's easy to do it, relatively speaking, with elements. But how would you do it with molecules? Okay? I'm not going to, just for time constraints, I'm not going to be going through this, but you can actually develop, with a consistent numbering scheme, a molecular periodic table for diatomic molecules. You can actually make every single kind of diatomic molecule, just like every single possible element, and you can arrange them in a way that not only their electronic structure makes sense, but their other facets make sense. So for instance, some of you may know that fluorine here is the most electronegative atom. Electronegativity increases as you go right and up the periodic table, okay? In other words, you can make a diatomic molecule periodic table that has trends like that, and you can make it consistent. I'm not going to go through that, but that was work done by Dr. Hefferlin and Kong years ago. But the point is it gets much harder, and the work that we're doing right now, finished, deals with that, in triatomics though, not diatomics. Okay, how do we go, where do we go from here? This is the big result from 2 years ago, and basically we saw something that no one had ever seen before, and it looked so pretty that a lot of people didn't believe it, and it started us on a new path into trying to extend it to triatomics. So let me explain this. As I explained, the Frank-Condon factors are the relatedness of the probabilities of transitions between higher energy states and diatomic molecules transferring to lower energy states. So if I have a particular diatomic molecule, and I start in a higher Morse potential, and I have a lower Morse potential, and I have states that populate that Morse potential, I can start, for instance, in 5, and the question is where will I transfer? what's the most probable one to transfer to? Well, if I transferred from 5 to 5, the probability of that transfer occurring is 4 times 10 to the negative 1, 40%. But if I went down to the ground state, or sorry, the one right above the ground state, it would be for this particular case, one right above the ground state to ground state would be 80%, okay? And it's really interesting because these are called Delandre tables. And if you do Delandre tables, if you make these transition things for every diatomic molecule, they all have this minima, maxima along the diagonal. And some people would say, oh, that's not that big of a deal. Well, it is if you look at it in a different context, in a parabolic space. Because these parabolas are actually the outline of the highest order transitions. And then this red line is the Morse potential overlapping that space. And that structure occurs across fundamentally every diatomic molecule. And that's a structure that no one's seen before. And so this reinvigorated us and was kind of like, oh, maybe we can do something with Frank-Condon factors for triatomics. But the issue is that there aren't Frank-Condon factors that are measured for triatomics. But what are measured are the vibration frequencies which are related. So we're going to employ this for what we want to do today. And so from here, I'm going to breeze over this because it gets really complicated, and actually most of our time was spent in data collection. The point is that there aren't enough stable molecules that you can make on Earth to get all of the periodic trends that you need. Diatomics you can get through with a lot. You can't make every single diatomic, but you can make nearly every single diatomic for the main groups up to about the second or third row. You can't do that with triatomics. The stability just drops off ridiculously. So even if you go to the National Institute of Standards and Technology and you look at their huge encyclopedia of every single kind of molecular data, there's hardly anything. There's only probably, I think there's like 600 triatomic molecules, which is a lot for the second and third row molecules made from triatomics. But the ones that are possible are something like 8,000. Okay? If we go to Russia and we commandeer their Soviet-era encyclopedia, which actually Dr. Hefferlin, being an ambassador to Russia during the Cold War, got, even that is severely lacking, and many of the same data exist here. If we go to the principal theorist of small molecules, Hertzberg, who won the Nobel Prize in the 1960s, I believe, for his work on small molecules, even his stuff is lacking. So we have to go, and then if we go to Handbook of Physics and Chemistry, the second Bible for us, it's, again, incredibly lacking. So the point is that we have to subsidize this somehow if we actually want to get the behavior of all of this as a system as a whole. And we do that with computation. That's really complicated. I'm not going to go into that at all. That's a whole other thing. I've spent the last 2 years of my life doing basically nothing but computation, so I'm just going to focus on the big ideas. I want to just shoot myself sometimes. But I don't like being in a dark room. But the point is that the computation is entirely necessary, and I'm going to breeze over that, but the point is that we have to subsidize it somehow if we're going to get the behavior of the entire system. That's the point. Okay, here's what all the data looks like. So, if I make every single triatomic molecule made from row 2 and row 3 of the periodic table, and I then search throughout all of the literature and all of the NIST data and every book that we can get our hands on, that's about 10%-ish of all of our data. Everything else has to be computed using quantum mechanical calculations. So here's the consistency. Don't look at this side, it's horrendous. Look over here. So the point here is that if you look at the consistency between the computer and other computer calculations for individual molecules, the average over all 8,000-ish species for us is 2.4%. In other words, the computer is pretty consistent. If we ask it to generate a molecule from one program or another, they agree. If we ask the experimental data, we hope it would agree, and it does. There's very low percent difference there. If you ask what the percent difference between the calculated value and the experimental value is, it's between 15 and 20% usually. Now, over on that side, that's the scary side, okay? We don't go there very often, but the point is that there is a lot of range. So there are places that exist in this higher dimensional tons and tons of molecule space that some of these are just ridiculously different, okay? They'd have nothing in common. The calculations and the experiments diverge completely, okay? And then sometimes the computer isn't even consistent. The way we mitigate that is we throw out the ones that we know don't look right. That means that we have to go through a lot of data hand by hand because you can't write a program that qualitatively is able to really tell from a simulated standpoint whether or not it makes sense. Okay. The point is that we have data and we can make it consistent if we get rid of stuff. So after we get rid of stuff, the choice is for us to either go home and cry or to go on and figure out some way of arranging it. So how the heck do you arrange this large set of data? Well, we choose to do it in a very high dimensional space. So here's the math for you guys. So here, this is a nice two-dimensional array of all the data for every element in existence. And we can pick out trends, going left and right and up and down all the time. But the issue is that doesn't tell you all the richness of the data necessarily. And it definitely won't when we go into the triatomics. So we simplify our life, okay? So again, if we only look at the first two rows, so ignore helium, ignore hydrogen, ignore all the lower stuff, definitely not the transition metals. And you only look at the main group and you look at the first two rows. We can get a numbering scheme. And we can get this numbering scheme from the left atom, the center atom, and the right atom. And all we need to do is look at the group number. So chemists like to count over the middle like I do as well. And so they call this group 3, 4, 5, 6, 7, 8. Just call it that, okay? So the main group can be organized with a numbering scheme. And I can then make a coordinate from these left atoms, center atom, and right atoms using those numbers. And I'm going to go a little bit in formula here. I had to draw it, okay? So if you define a coordinate with 3 numbers in a discrete metric, you get a nice little grid here with nothing in between. It's not a continuous axis. And then you can populate it with a set of points, and you can ask yourself, okay, what does that point symbolize? Well, that point, the issue is, contains a lot of stuff because it doesn't contain just one molecule with that group number coordinate. It actually contains an entire set of molecules that have the same group number coordinates. So remember how I was mentioning sodium and potassium before, right? They have the same group number. They're in no way the same element. So we have to make some use of extra dimensions now in order to make this point unique. So one of the best candidates would be, why don't we just use row numbers? Why don't we make another set of coordinates here and span a 6-dimensional space rather than a 3-dimensional space? So if I do that, I'm going to make another set of coordinates along this axis And now everything will be unique because I can go from 1 to 3 and I can make my axes, I can populate them with row numbers, and now I can get another point in row space. So the point I wanted to say here is this: there's a group space and there's a row space. And they each go in orthogonal directions to each other in a higher 6-dimensional space. This will make sense more in a second. The point is that you have to do it uniquely every time. So then it becomes the question, all right, I have all, ooh, whoa. That isn't right. This is why Apple just needs to go out of business. Okay. Windows. Okay. So those are supposed to be subscripts. And that's supposed to be an apostrophe. But okay. Okay, so the point is that I have coordinates. I have C1, C2, C3, R1, R2, R3. Okay? I now have a unique point in 6-dimensional phase space that I can populate with some kind of space, with some kind of value. And those values I can populate with are those vibration frequencies, those bond lengths of the 2 bond lengths of the triatomic molecule, a third bond length which we can calculate from law of cosines, and then we can just say, okay, if I have a triatomic molecule, is that bond number 1 or is that bond number 1? Which one is which? Maybe the thing that's more periodic is actually the separation of the outer atoms, rather than naming one or the other. And then I can talk about the angle. And we call this whole 13-dimensional thing the triatomic space. And we can populate this 6-dimensional space with fields. And these are continuous fields of vibration, frequency, bond, length, and angle. When we do that, we can make some interesting stuff if we choose to make slices. So we can take a slice of this huge 13-dimensional object, and I can just choose, why don't I let C1, C2, and C3 range, and then I choose what R1, R2, R3 are, and I choose which one of these to graph. So I can, these are all supposed to be centered too. Anyway, okay. If I choose to do 2, 2, 2, we call that the 2, 2, 2 space. Okay? So that's everything from row 2 that's possible. And then I'm going to let C1, C2, and C3 range from 1 to 8, and I can choose to graph these different things in that space. I can do the same thing with 3, 2, 3, where the outer atoms are from row 3, and the inner atom is from row 2. Okay? So then we can make a big, big space. This is actually a 7-dimensional object. Okay? You're looking at it in 2 dimensions. That's really cool. So if I let this axis be the row axis, this axis be another row axis, and those form the outer row axes, and there's my central atom axis, okay? I can then populate that discrete space with segments of discrete spaces. So I can populate it with group spaces. So I can look at 3-dimensional coordinates of 3-dimensional coordinates, if you want to think of it that way. Now, technically, that's incorrect. They're not boxes. It's a little bit more complicated because some of these are very symmetric. So I mentioned right here 2, 2, 2 and 3, 2, 3. Those happen to be what we call symmetric spaces because if you look at this object here from above and you look down on it, you'll see that actually there are molecules that are actually mentioned twice. In other words, all the same molecules exist on one side as they do on the other. So this side here is the exact same side. This right here is the exact same as this side. But there are ones that are actually squares. Sorry, not squares, cubes. Because all of the molecules are unique. Okay? So it's actually not a cube. It's actually a triangle. This was one of our first drawings. It ended up being wrong, but it's a nice way of visualizing it. This is actually what it looks like. Okay? So you can do the same thing with rows. Basically, this is that big box, and you can see that, oh yeah, there's stuff that's repeated. So again, it's not a square, it's not a cube of 7 by 7 by 7, but instead, it's actually a triangle. And we can just choose to take this upper one and not have redundancies. But the unique spaces are the symmetric one, the unique spaces are the asymmetric ones. So only these have triangular symmetry. Everything else are cubes, okay? Here's what we can do with that. We can visualize all the fields of the data. So if I choose to populate it with the field of vibration frequency 1, or 2, or 3, or bond length 1, or bond length 2, or that L prime thing with the cosine law, then we can make some interesting stuff. And I can choose to let C1, C2, and C3 range, the group number coordinates range, and I can develop some very interesting things that we call matryoshka, okay? Matryoshka are Russian nesting dolls. So when Dr. Hefferlin went to Russia, he never really came back. But the point is that we can make these nested structures. And we don't ask for them. They just come out of the data. And the crazy thing is that he predicted it. So here's what they look like. This is new 1. So this is the first vibration frequency mode. Okay? Let me explain what's happening here. Every point here represents a molecule. Okay? And it's a unique molecule because I've stipulated that's only from 222. It's only from row 2 elements. Here's a range of the vibration frequency data. Blue is really, really low. Red is really, really high. And if you look and you ask and you say, I think that those color fields, that's what we call these color changes in the points. If I look at those color fields, they look like they're increasing inwardly. In other words, as I move inward, it looks like it's increasing in value. And then if we say, okay, forget the discrete space, let's make the space continuous. What happens if I say, okay, take these points and make a contour, make a big surface that surrounds and cuts through these points using some very complicated statistics, but anyway, the point is that I can take a discrete thing and I can make it into a continuous thing by interpolation. And then I can smooth and other things. So if I look, the outermost surface here represents the low vibration frequencies. That's the orange surface. The innermost orange surface is the high vibration frequencies. This is for new 1. This is for the first vibration frequency. And it gets interesting when you ask it for new 2. Different vibration frequency entirely. Remember, I'm doing this versus this, okay? But it looks the same. Don't ask about this one. This one's really weird, actually, but that's another thing. This is new 3. Okay, new 3 is harder to deal with. And then I can ask what the angle looks like. It's really, really patchy here, but it actually has the same structure of the outermost being the highest and the innermost being the least. I can ask what the first bond length is. I still have these nested structures. I can ask what the second bond length is. And I can ask what L3 is, the third, which is the law of cosines. And all of them still remain nested, okay? So that looks really cool. And it's a qualitative example of what we would call periodicity. We have repeated behavior across an entire set of molecules. And we didn't ask for it. We just imposed a structure, and there it was, okay? But just because you have qualitative data doesn't, in visual form doesn't mean anything. You have to do your statistics, okay? So particle physicists would say 5 or 9 or however many sigma. We're not that crazy, but we do need to do some statistics. And so we want to investigate whether or not all of these things are related. Because the ultimate thing would be that if one molecule in this space was at all related to one molecule in this space, then there would be very little difference in their behavior, okay? So if I looked at lithium, 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 and I asked, is it at all similar to sodium, sodium, sodium? Well, chemically speaking, each of the individual elements, are entirely pretty much the same. But when you ask that question in the realm of molecules and using quantum mechanics, it gets really, really hairy because it's a many-body problem. So just because the subset of your structure works. Doesn't mean that this more complicated structure will act the same way, okay? So here are the statistical results. Oh my God. Yeah, interpret that. Okay, so there's a lovely formula that I spent like 15 minutes writing in here talking about how I'm going to use one space and relate it to another. So anyway, okay, the point is that you can do a percent difference between a normalized mean percent difference between every molecule in every space. And you can ask the question, are they related? So it's basically the ultimate measure of the periodicity because I can talk about one thing, is it the same thing as the other? If it's normalized, in other words, if I normalize it to the highest value possible. If I do, then what ends up happening here is that I can sum all these differences together and I can make a mean for each individual space by relating one space to all the other ones that exist. If I do that, I get all of this stuff. What I want you to notice is that if you can read it, they're all really tiny, most of them, okay? The angles and the bonds are a little bit weird, but all the vibration frequencies, the things that relate to those Frank-Condon factors, the things that relate to the quantum mechanical states, those are the things that have ridiculously small normalized percent difference. In other words, if I start in 222 and I ask what are the differences of all the molecules here from all the molecules that they have in common with 223, everything looks the same. That's really weird. And it's really interesting because that allows you to do some really cool things. Because if every molecule is similar to the other, and I can figure out a way of looking at just one set of molecules, then I wouldn't need the others if they all act the same. So I have to compare these differences to, for instance, maybe like a standard deviation. And the thing that confirms it for us is that the differences between the molecules are about 100 times smaller than the standard deviation, the spread in the data over an entire individual space. That makes it significant to us. So that makes some interesting conclusions. Because if that's true, then we have really a fundamental space. And that's important for this reason, that if you know all of the data for one space, a fundamental space, a simple one like 222, what it means is that I could extrapolate what all the other spaces would act like. So then I can go back to my supernova and I can say, oh, okay, I know the relatedness of this number of molecules and this one. Well, maybe I can identify these guys over here with the simpler ones. It's a nice, easy way of doing things. So it's an extension and an extreme demonstration of what Mendeleev called the periodic law, which is that we have repeated behavior and we're using the same numbering scheme as Mendeleev. We're extending his periodic table entirely to 3 dimensions. So why is it cool? It's cool because it's, 13-dimensional space is kind of cool. But also it's fundamental chemistry that no one has ever talked about before. And also, because we can compute these, it does point to stability under specific conditions, and that can have an application in astronomy. And also that the former chemical generalizations don't hold. So that's the big result. I just want to have a really quick thing to thank my colleagues, especially Dr. Blake Lang, who I couldn't talk about any of his work because he did all the computation. Dr. King Cavanis helped with some of the visualizations, and also my research assistant, Devin Nash, really, really brought it home in these last few months. So thank you, guys. All right, so I know that that went over a little bit, but if you guys have any questions or if you want to see me afterward, feel free.
Questions?
It is Friday afternoon, so I understand the naps are coming. Yes?
So on your diagrams of, can we go back to slides? See those diagrams there?
Yeah.
Explain what again, could you say is meant by going inward into the diagram?
So going inward would be from every side go inward on equally. So if I choose 4, 4, 4. So if I look at this guy here, this is interesting because this is the vibration frequency of 222 molecules. So basically what that means is that the most stable species for row 2 molecules, okay, are in the center of this graph. And that makes sense because if you think about what happens around row 4 and row 3 and row 5 and 6, okay, those are the really, really stable ones that we see all the time. So necessarily they also have higher force constants, et cetera. Basically, the faster they vibrate, the more stable they are. So carbon and oxygen, et cetera. Hopefully that kind of made sense.
Yeah, I guess what I was saying is, so the 222 is referring to the rows and the space is your column.
Yeah. Mm-hmm. Yeah. Yeah.
Could, I noticed when you were talking about like 6-dimension, 15-dimension, could this stuff also be represented in a matrix?
Yeah. And yes. We didn't, ideally, if you wanted to do it small, you'd use a tensor, but yes. Basically an array is a matrix. So that's how you do all your computation, is you actually take this whole big object, and if you assume it's in a certain order, then you can do operations on it. Yeah, so that's how we got all this stuff. Any others? Yeah, oh, I didn't know if you raised your hand or not. Sorry. Oh, okay. Yeah.
What year in your undergrad did you start working on this stuff?
So this has been 2.5 years now. So I had just ended my 3rd year of 5 years. Yeah. So it was technically my junior year, but not exactly. Yeah. So that was in the summer, actually. So, yeah. That's one thing, if you guys ever have the chance to do REUs or summer internships of any kind, go for it if you're interested in the problem. I at first wasn't interested in this problem, but it got really interesting really quickly, so it kind of consumed me. Yeah.
These three-dimensional spaces are representative of the row subset of for example, 2 to 2. This could be an atom from row 2 and another atom from row 2 and another atom from row 2.
Yeah.
And are these trends similar for also different other
Yes. I just showed one. In the final paper, there's a huge table of graphs that's every single one of them is graphed, and they all look similar. And then the statistics confirm that. So if you look at, for instance, I know you can't see it, but this is starting in the 222 space. And if I relate it to the 223 or the 332 or all of the other ones, they all behave the same way, if you look at the ones that are common between them. And actually the crazier thing is that you can do a fit. You can treat this one as the fundamental space, and if you normalize all of the data, I can multiply this whole space by a factor, and I can get the other ones, which is kind of interesting, to about 15 to 20% difference, which is the experimental to PC difference. So, yeah.
So in this big space, what directions or slices retrieve the two-dimensional periodic table of the elements?
It would just be the slice of C1, C2. So it'd be a two-dimensional slice. But it would, actually, it would actually technically be a one-dimensional slice because C1, you would need to put them together. So if you looked at, this thing here, where you have your rows and your point, technically speaking, I would need just one of these because one of these ranges from 1 to 8. And then I would need one of these. And then I would put them together. That'd basically be the way of doing it. And then you would get this whole thing back out.
What does that mean in terms of the actual, molecular, the molecules? What kinds of triatomic molecules would you be looking at in that slice?
You wouldn't be.
Okay.
You would effectively, and there have been, I didn't put in some stuff because of time, but basically there has been work that was done under Hefferlin, where they did exactly that. They actually basically pretended that this point has 20 molecules in it, and they all have the same row number or the same group number or something like that, and then you just average all of them. So there's some really nice work that was done by Dr. Blake Lang that said if you take a three-dimensional space where the axes are heat of formation and then just the central atom group number and then the number of electrons that are in the molecule, then you can actually make these hill-shaped surfaces, and they're hollow inside. So, but the point is that on every one of these, where C2 is allowed to range, the central atom number is allowed to range, at that one point, there's like 15 molecules. And then you just take the average of all of them. And then you still develop structure. But basically, one of the things was that we didn't want to do that level of averaging. We wanted to look at the individual behavior, and because that's a better measure of it, of periodicity. Yeah?
What would be the next stage in this research, and who's going to do it?
The answer is no one. There is a possibility that Devin, my research assistant, who's still at Southern, who actually switched to physics because of the experience, which is really cool. He was engineering. He got really into it, and my hope would be that he could continue it. The issue is that I'm not there. I'm not going to be pursuing it any further, and no one else is really interested in continuing it either at the department. The work is unique because there is a conference that meets every couple of years called the Conference on the Periodic Table, run by Eric Sherry, who's out of UCLA, who's very much a chemical philosopher in some way, looks at the history of chemistry and so on and so forth, and thought the world of Doc, et cetera. And he's been a principal progenitor in the field. But other than really him in the United States, there aren't many. So it's a dying breed of research, which is interesting because it's nice to be able to finish off on a high note in some way with this stuff, because after Doc died, I kind of got really into it and found that he was wanting to keep it small because he wanted to make the conclusions and make sure that they were sound. But what I found was that he just wanted to do nu 1. He just wanted to do the first vibration frequency. And we found that it works for everything. And so he hadn't dreamed of that level of structure, which in some way is a really good end to it, because we've done everything and we've found almost everything. the limit is that you can't go beyond row 3 computationally. Because after row 3, you get all your d orbitals in there and it just complicates things. And you can't do the many body problem as well anymore. And so unless we were to write the code ourselves, which would require a few PhDs, you couldn't go beyond what we've done, basically. So.
This level of complexity is able to, like it just went from pure orbitals to
Yeah.
like, okay, this is complex enough for you.
Yeah.
Oh,
Yeah, exactly. Yeah, after you add the d orbital, and that's why the transitions are a problem, because, I mean, the transitions are the characteristic of the d orbital. So and that's what allows us, to have all the wonderful chemistry that we have with metals. So it's very important, but it's just hard to do computationally. You can make tons of approximations, but it's hard to do from a very, it makes sense if you're in condensed matter theory, because you have a ton of them, you have a ton of atoms, and you can say, oh, they all act this way. But if you're looking at a very, very small subset of atoms at just the 1 molecule scale, those approximations go out the window, and you can't do it anymore. So unless there's a new program that comes on the market, it's hard.
Okay, let's give our speaker another hand.
All right.
It's fantastic. It's just the right level.
Good.
Just right.